Yeah. All right, welcome everybody. Welcome back to the new semester's Dream Seminar series. And I'm delighted to introduce the first speaker, Professor David Broman. David is a full professor at the Royal Institute of Technology in Stockholm, Sweden, which goes by KTH. He, before that, way back, he got his PhD from Linköping University. And after Linköping came the most important phase of his life, which is he came to Berkeley and spent, I think, somewhere between 2 to 6 years at Berkeley in different roles. And I had the opportunity to work with David at the time. Had great fun working on a range of different topics. Then he went back to Sweden, and he's been doing really amazing work in a combination of 3 different areas. On the one hand, programming languages and compilers. Second, real-time systems and cyber-physical systems. And on the third hand, probabilistic systems and machine learning. And all of these topics come together in the topic that he's going to talk about today. But his work has received many awards over the years, both in research and in teaching. So really delighted to welcome back David to Berkeley, and looking forward to your talk.
Thank you. Thank you very much, Sanjay.
Join me in welcoming David, please.
Thank you a lot for that kind introduction. Today I'm going to give you kind of an overview of some of the central parts that we work on in my group. So it's going to be about this framework, connecting how to write domain-specific languages and how to engineer that, and then connecting to probabilistic programming. Just see here, how many of you are kind of familiar with probabilistic programming as a concept or are using it somewhere? So not so many. Okay. And I have a little bit of an introduction to probabilistic programming part of it, so that's good. Okay, so first I want to say a few words about the research group, what we're doing in the area. And Sanjay actually almost introduced it. And then go into this framework, which is a kind of a new framework that is open source and available. And then connecting this to probabilistic programming and how we are actually using this framework as part of this when we're doing probabilistic programming. Right, so this is my group, and we really work in the intersection of 3 parts. So it's programming language theory and compilers. We publish in this kind of venues, and then especially also on, we say, machine learning, we're focusing on what we call probabilistic machine learning, so connecting to Bayesian theory. And then most of our problems are related to real-time systems and cyber-physical systems. But there are also some other collaborations that were started in things that are not really cyber-physical systems. So central for this is models and modeling. And you can think about when we're modeling something. We have a system, so we make an abstraction of that. But you can also view it in a different way. You can view it from a scientific point of view or more an engineering view. So in the science view, the system already exists. It can be a biological system, can be some physical system. And then we are using this to model it. So we are adding abstractions to be able to reason about it. Whereas the engineering view, it's kind of the opposite. We often have a blueprint. We are creating something, an abstraction, and then we're using that when we are constructing the system. So both are valid viewpoints, but they have some different properties. So why do we do that? Well, we would like to be able to do experiments or do some analysis on these models, these abstractions, to be able to learn something. To get some insights, sometimes it's cheaper to do that before you actually build it. It can be too dangerous. You don't want to make experiments on real nuclear power plants. It's better to do it on a model before you test something new. It may not exist, or it's easier. And what we do then is to facilitate this and create domain-specific languages and approaches to create domain-specific languages, where the overall goal is to raise the level of abstraction, to make it easier for the end user, at the same time to generate, have, and get efficient compilers for these kind of languages. And sometimes it goes hand in hand, and sometimes it's kind of contradicting each other. So when we talk about models here, we don't talk about graphical models, or is that you do something graphically. It's rather mathematical models, typically expressed as programs in different ways. Can be more declarative programs or more programmatic. And one thing, way of thinking about this is kind of programmatic models. So what do we mean by that? And so if we have a programmatic model M, that is then a computer program where its behavior describes an abstraction of some system, let's call that S, such that we have some analysis technique A can be performed on M to answer questions about S. So this is, I would say, is general for ways of doing modeling, but the specific thing here is that programmatic modeling, programmatic models are basically programs and can be very expressive. We'll see that especially in probabilistic programming, what that means. All right, so let's go into this framework. What is it? It stands for, Viking stands for the meta Viking. The meta is it's about meta programming, programs that generate programs. And Viking is because it's developed in Scandinavian and we wanted to have Scandinavian touch. So it has nothing to do with the mic. All right, so the objectives and they are, which are partially already fulfilled, but they're always refinement. You know, this kind of project never ends, kind of. It's a platform for constructing heterogeneous DSL. So I'll come back to what I mean by that. It's got a polymorphic type system, so it's based on system F, and it's got type inference. So we are using an approach that's been developed in Edinburgh. It's bootstrapped and retargetable, so it's written in itself, the core language. So the whole compiler is written in itself. It produces highly efficient code. So this is one of the purposes with it is to be able to have high performance solutions. And another thing is that we target both real-time systems, so that you compile for something that should be able to run in real time, but also applications where you want to do, for example, an inference as a batch. You compute something, maybe it takes days, and then you get the result. We'll see that that is more in, for example, the biological areas that we are collaborating with. There are also the purpose to be able to target different kinds of platforms. So this is also in heterogeneous in the sense that you want to be able to compile to different kinds of platforms, GPUs and CPUs, for example. And it's really a research platform. And it's also open source and available. And we typically submit code and then make this available directly. So it's a vision paper that I wrote a couple of years ago, trying to outline what are the, what are we trying to do with this. Now, a couple of years later, we have done a lot of things, but of course not everything is done yet. So the idea is that one part in here is about interactive modeling. The second part is about language fragment, and this I will dive into a little bit more. So how many of you have taken compiler courses? Someone. So I hope you bear with me when we're coming into this compiler part. So the idea here is to be able to have language fragments you compose together. When you're creating new languages, you don't start from scratch, but rather you create small fragments and then you can compose them together and build up more and more complex languages. And the third part is about this compilation, to be able to compile to different platforms. And we also do work on where you try to do this mixture. So some parts should live on the GPU, some parts on the CPU, and that you can easily specify what should be with where, so make it easier to accelerate your programs. So related work, of course, when we talk about domain-specific languages, there are a lot of things done. I mean, the most traditional way is to just write from scratch, take like the Dragon book and learn about parsers and type systems and generate your own DSL, but that takes a lot of time. So that's why embedded DSLs are pretty popular, where you embed the DSL in another host language. And the benefits, then it goes pretty quick, but it's also the problem that abstractions from the host language, say that it's Haskell or Scala or something else that is pretty popular, the abstractions kind of leak into the DSL. So you have to typically know the host language to be able to use the DSL, which is not always a good thing. C++, has more this kind of pre-processing is another approach, and then we have this kind of language workbenches where you try to make as a whole environment to make it easy to generate the domain-specific languages. And I would say miking is more in the last part. It's not embedded. Previous work we did was called Modelize, was really about embedded DSLs, but we also experienced some of the problems with embedding. There are pros and cons. So if you look at this, the overall toolchain here, center is this core language that's called MXPer. So a program internally is always just an expression. So it's a functional style, so it's a timed functional language. And we try to design this MXPer to be very expressive, but still minimalistic. And that is part of the challenges. Then we have this called MLang, which is the language is an abstraction, so it can always compile down to MXPer. But this is where you define different language fragments, how you compose language fragments together, and then in the end, it always becomes an MXPer that you then later compile. So you have these things together, and that's what we call MCore. And then you can compile that down to different targets. So we are the main compiler is piggybacking on the OCaml compiler for efficient code generation, but we also have JavaScript, and now people are working on a JVM backend and so forth. So the key thing is this language fragment. So language fragments builds up the whole program. Actually, the whole compiler is composed by language fragments. So we define the whole compiler using language fragments. So if you know about the Lambda calculus, there is a fragment for lambdas, there's a fragment for records, there's a fragment for let bindings, and so forth. And then when you want to construct a language, you just pick and choose which fragments you want in your new language, and then you base it on that. If you want to create a DSL, then you can pick some fragments that are useful that are already in libraries, and then you create your own new fragments that are relevant for your DSL. So we'll see for the probabilistic programming, you have then random draws and observation statements, for example, that you then create different fragments for. But you don't have to reinvent the wheel and handing out everything about the functions and so forth. That is kind of, you can just pick that from the already existing libraries. So if you do in DSL, then you maybe extend it in some way. But if you want to be able to compile it, then what you do then is to lower it down to MXPer. So then you compile down your newly added fragments, the logic there. Then you translate that down to MXPer, and then you can use the rest of the toolchain to compile it. So that's why you then can create DSL, add your extensions, but then you don't have to write the whole thing about the backend and so on. And then to be able to have a syntax, of course, you need to have some syntax extensions. And this is an external DSL, so it's not embedding. So it's basically that you describe this using grammars. And we have some new way of doing this that we presented at POPL a week ago, so last week in Boston. So I will say a few words about that. Okay, so miking then, if we look at the MXPer, the core, it's a functional intermediate language, so it's typed and functional. It's polymorphic, as I said. It's polymorphic, statically typed. This is important, especially when you're compiling down to lower languages that requires types. The design choice here. So I mean, we use this framework for doing research. So we do different topics, and all my students kind of contribute by doing research on different topics. But then, of course, there's a lot of engineering work here, and some part and a lot of design choices. Which design choices is not always scientific, right? There are very different opinions and thoughts, but it's still very challenging to make the right design choices. So what we try to do here with this intermediate language is to have the concrete syntax so that you can view it to be as close as to the abstract syntax. And if you have not taken compiler courses, what is abstract syntax or what is concrete syntax? The abstract syntax is the internal representation. Sometimes the abstract syntax can be an intermediate representation internally in the compiler. So we want to be close, because when you look at programs in this core program, you should be able to understand directly what is the internal representation, and then it cannot be too much syntactic sugar on top of it. It tried to be small, but also complete. So it's got a lot of useful features that you typically need when you're generating languages. So this is just a small program in MXpert to get a feeling of what it actually is. So here, this is a data constructors. So this is an algebraic data type, a tree. So just an example with nodes. So it's binary tree here with nodes and leaves. And we happen to be able to have integers attached to the leaves here. So if you're used to functional programming in Camel or Haskell or something, this should be familiar. If you're not, then it might not look that familiar. Okay, so this is then an example of this a simple program that is recursively traversing this tree. And here are some code just giving you a test case, and we have also built in from the beginning a unit testing framework. So it's very lightweight that you can write. So this is actually how we document most things. It's just writing small unit tests next to the function, and it's been very useful, especially since in the beginning we didn't have a complete type system. And if you don't have type system, you need to have tests. So it's been kind of going hand in hand all the time. So this is just to give a flavor of what does it look like, this MXpert. And the idea is a little bit same as in LLVM, that you want to have a small intermediate language so that when you do transformations, you transform into yourself. So everything goes in and transform into MXpert and go forth. So this is how when you write in compiler passages, you always operate on this expression language. But it's completely different, of course, from LLVM in the sense that it's not the SSA form. Okay, so that was the MXpert language. Then we have this MLang language where you describe the different fragments. So the key idea is that you compose together fragments when you want to create new languages. So we'll have a very small toy language here that probably, but it's working code. So just show the principles. So here you have an arithmetic language, arith, I call that. And there are basically two things in the language framework. You have the syntax, the syn, which is then the abstract syntax. Here we describe a number and a value for operation for add. So this is very close to an algebraic data type. And then you have the semantic functions where you can do pattern matching on this and describe the pattern matching and give the semantics basically. So the syntax and semantics of a language fragment. And you can create whatever semantic function you want. So this is very close to a functional programming language. If you can use it, then you say, okay, I use this in MXpert and just say that I use this language fragment, and then I can write the program. And in this case, I just wrote a test program that tests this expression. Okay. Now let's say that you want to write, you have another language fragment that is kind of independent of this, where you define Booleans. So Boolean language where you say that you have Boolean values and you have an if expression. That is your syntax. And then I have the evaluation function describing what is happening. So this will be kind of like a big step operation semantics if you're just going to find it in this way. What you can do then is if you want to have a new language, you can compose these fragments together by just saying that, okay, you have a new arith bool, and I'm building that up by composing arith and my bool. And then we have a new language, and then we can use that as the composed language. And there are certain things that is important when you're doing this, is, for example, that pattern matching must be order independent. So the order where you're composing shouldn't matter. So we have a special way of handling, so it's pretty sophisticated pattern matching system in this language. And basically, most things are actually pattern matching. And doing like this, we have then in this language fragment, there are a lot of transformations that are needed when you're writing compilers and engineering languages like ANF, a normal form, CPS stands for continuous pattern style. not for cyberphysics in general. Lambda lifting and so.
Do you take questions during talk or after?
I can do that.
I was wondering, how do you deal with operator overloading?
So operating overloading. So we
Yeah.
don't have in the core language should be simple. So it's not supporting operator overloading.
Because if you have to do the pattern matching in a certain order, then obviously that poses problems, right?
Yeah, no, you don't have pattern matching, you don't have operator overload at this level. You can of course define language on top of it that has that, but it's not. So the core language is really trying to be minimalistic, although not too minimalistic, because if you could write everything just having lambdas and beta reduction, but it will not be very useful.
Gotcha.
Good question. Okay, so this is the idea, and then the whole compiler is built in this. So we have tons of then fragments that are composed together to be able to then form and make it easy to extend it in different ways. So that was about the language fragment, which is kind of a core part. Then I want to say a few words about this recent work on this resolvable ambiguity with the parsing that we just published. So in a traditional approach, you have a parser and you have some input program, and typically the output would be some abstract syntax tree in your compiler. And if you're taking a compiler class, you are often taught that the grammar must be unambiguous. If it's not unambiguous, you have to rewrite the grammar and figure out and so on. So that's how it is. I mean, you cannot find any textbook basically saying anything else. What we say here is that might not be the best idea. So instead, we introduce this concept of resolvable ambiguity, so that you have a parser, but your grammar is then partially ambiguous. I have a few slides with more motivating examples, but I can just explain the key motivation. And that is that in some languages, when you're writing constructing a language, it might be obvious what is the precedence and associativity and so on for certain operators. We know with plus and minus and is childhood what is the precedence. But if you're creating new languages, domain specific, it's not obvious what is the precedence. How should you disambiguate this particular program? Or if you're constructing languages, in many languages, you can have you create operators in one language, but someone is doing, and then you have another language, and then you're using both these languages together. What is the precedent then? It's not obvious at all. So the idea here is that instead let it be possible for the language designer to say, okay, this part is actually unambiguous. I don't say what is the precedence, and then let instead the programmer, when he's compiling, if he didn't specify the precedent, then specify it, because the end user knows what it means. And then in the end, also, since you put that explicit, it becomes also more readable for someone else, because it was obviously not clear. But you don't want to do that for everything. And that is the language designer's choice. Where should you do this? Well, you leave some parts ambiguous and the other parts unambiguous. So that's the kind of idea. So you have the input program, and if you're compiling that, it can generate many abstract syntax trees. That means that it's ambiguous, right? Then you get an error message telling you, well, you can solve this by putting parentheses here or doing like this. These are the alternatives. What do you think is the correct in your context? Because both can have be a correct program doing something, but you have to make the choice what is actually correct in your context. And then the end user changes that and then resolves the program. So this is the resolving part. So that is all good. Of course, if you formalize this a little bit, if we say that we have a parse function called parse that sets P as input a program, and then generate a set of abstract syntax trees, then we say that the program P is ambiguous if it exists two different parse trees that are not the same. And it's ambiguous. At least two. We say that a program P is resolvable if therefore all ASTs, when you're parsing a program P, access a P prime So another program that can be rewritten by the user, such that when you parse this P prime, you only get one ASTR. That means that it's not ambiguous anymore. So the resolvable ambiguity means that you can rewrite the program such that you can resolve it. And the static resolvable ambiguity problem is how can we guarantee that you cannot construct a language that does not have this property? And you typically have to constrain it in some way, and we have then developed a solution for that. And in the first paper we had on this topic, we introduced this idea about having resolvable ambiguity, but we checked it using property-based testing. So it was in the loop we're testing that it was resolvable, but it doesn't give any guarantees. And then in the paper that we just published, that's where we give these guarantees. We have a formalization and a cock proof and so forth, and also show that it actually works in practice because we rewrote OCaml's whole expression language, which is kind of huge, and show that it's the slowdowns are marginal in milliseconds. So it works in practice also. That's kind of the key idea of this approach, and then we have in the miking framework a way to specify these grammars and so on, and use that for generating the domain-specific languages. That's the idea. Okay, so there are some different works going on. As I said, this is a kind of research platform that I'm using mostly in my group, but I've started to have contributors outside the group, which is great. And also I'm interested in applications that have a fit connected to this. So one part here is about equation-based modeling, that some of you that know my previous work was a lot about on this, where you model using differential algebraic equations for simulation. So this is an example in a more declarative way where you can write this model then saying that you have a world object, and then you kind of have this domain-specific construct saying put this in series with this dash dash, or then we have also, it's not shown here, but put this in parallel where I have another operator, and then you can compose together systems. Pretty declarative. I mean, so when you showed about Scenic, it's kind of the same thing. With minimalistic text code, you can make it very expressive. So this is kind of done a simulation when this is running. Part of this is also done in this previous work with Modelize. Another part that we are interested in is cyber-physical systems. So we are recently started to also build more systems. So we are not just doing it in theory, but also have physical systems. And why do we build them on ourselves? Why don't we just buy things? Well, we're very interested in knowing exactly the physical properties of these systems, since we are then modeling them using our DSLs for modeling, and use that also for training. So you kind of, in that way, generate data when you're training. And then another topic that I work together with people in phylogenetics. So this is completely, it has nothing to do with CPS. It's evolutionary biology. So this is basically how people in biology do research when they are interested to understand the history of species. You're sampling from some DNA from different species and then derive trees from that, and also to derive properties on these trees. And Bayesian methods is one of the standard way of doing it. So my collaborator is the one that's done this Mr. Bayes, which basically everybody used in this domain. And now we're defining a new domain-specific language that makes it possible to create new models. This Mr. Bayes was very like hard-coded for one model, but it's not, takes several years or a PhD to create a new model because you have to develop the whole new software. Whereas with probabilistic programming, the idea is that you can just define a new model as a small program. But then the challenge is to make the inference efficient. That's kind of the reason. So there's a web page that has some information. I mean, it's a work in progress as well, always. This is GitHub, and we also had our first workshop this fall. So it was kind of a little bit of a milestone for us. We had 50 people signing up and so on, both in person and in also. So I'm trying to get more also students involved in, contributing in different ways. Okay, so I just at this workshop, I just show it's kind of fun. We showed this robot here, and we did what we call robot charades. So people should guess what the robot is doing, and then it was more like a fantasy kind of what it was actually doing. So what is it doing?
Push-ups.
Push-ups. It was a kind of debate if it was push-ups or squats. It depends if you have legs or arms. So what does, and then we call it a spider, and people object because spider has more legs. Yeah. So I have another one as well.
What is miking used for in this particular application?
So right now it's not used at all yet. So now we have built a system, but we are going to use it for probabilistic programming to be able to control it. And so this is one of the line of work to be able to control, not at first it's not interacting with other things, but rather learning its own physical dynamics. So we are building now a small humanoid where the task is to be able to learn how to sit up, stand up, and maybe walk. So it becomes very much a balancing problem, be able to behave. So it's a little bit, and there we need to have training data, because you cannot do 100,000 trials in physics, and that's why we are doing physical modeling to be able to do that.
And can miking be used as a way to integrate multiple languages?
Yes.
Have you done?
So the languages at the low level, these language fragments, that's what we do now. If we're thinking about composing languages at the higher level, so to speak, that you define one language and then be able to just write, we call that nesting of languages. So you have a language and then you say, now let's use another language
I
as
think
part of
of like co-optimization, so that you have a language that can call,
right.
can foreign function calls to other code within other languages. Right, so P, for example, had that capability. You could write a P program, and then from P you can call C++ code.
Right. Yeah, there is a foreign.
Lingua franca has a similar polyglot nature.
There is
wondering if
there is a foreign function interface in
but there's advantage in so miking, if I understand right, provides you with this lower level representation that you can then take multiple higher level languages and then co-optimize them.
Yes. And one of the key thing is that you can reuse part that you develop for one language when you develop in the new language.
Right.
So we'll see here for the probabilistic programming part is one example. Okay, so let's jump into the probabilistic programming part here. So what is probabilistic program? If you have a normal program, you have some input. If you have a batch program, and you generate some output. A probabilistic program is then you kind of going in the reverse order. So you're observing something, which is the output, and then you want to infer the input, which would be the parameters. And this probabilistic program, you can view that as a programmatic model, a probabilistic programmatic model, which includes then your prior knowledge of the parameter that you want to infer and the likelihood. And maybe this looks familiar to some of you because it's basically the components that are in Bayes rule. So probabilistic programming is basically a way to encode Bayes theorem and then having observation and inferring data. And the prior and likelihood is that what you encode in the probabilistic program. So this is the kind of the traditional view of probabilistic programming. And the key idea, I mean, the dream scenario, it doesn't work always in practice, is that you really separate the probabilistic program, the model, from the inference algorithm, so that the end user do not have to understand how inference algorithm works. They just can focus on the modeling, which has turned out to be pretty challenging. I mean, for example, Jen and the work at the Vikash group at MIT take the approach where you try to always combine these to just kind of co-design the inference algorithm. And that makes sense in many applications. What we try to do in the Folinetics is to actually separate it so that the end user should really focus. But then we can make it domain specific because we are focusing on Folinetics, then we can make it more domain specific for Folinetics.
I mean, the end user is not focusing on inference algorithms.
Exactly.
Just on describing the model.
Yeah. I mean, some of the people in biology there, they are not really programmers either. So it's hard to make it. So functional style of programming a model is not the best way of describing it. So you can view this probabilistic program as a generalized generalization of Bayesian networks, and then you have different inference algorithms. And then you put this together and can compile then a program that should be efficient. And this is kind of the research part we are doing. How do we do this generation and get this really efficient? So you get some input data, and then you can infer estimates. And also important regarding Bayesian inference is that you don't get point estimates. Typically, you get distributions. So you always get the uncertainty. But you have to approximate this, and this is the challenge. So there's a lot of work done in this. I mean, we have these classic ones that are working on more Bayesian networks, like Bugs, Jax, Stan, infer.net, and so forth. Stan is one of the ones that is really used a lot today. Universal probabilistic program is kind of a generalization where you don't necessarily know how many random variables you have statically. So it's not a fixed number. It depends on the model when it's executed. You have this concept of stochastic branching. So, and it's basically you can encode this in any Turing complete language. So Church, for Noah Goodman, who's now at Stanford, was kind of pioneering this together with Cash and others. And we have web people, there are Birch, Jen, Venture, Edward, Pyro, many languages, blog here, and Scenic is a variant of that as well. And we developed what we call the miking DPPL, and D stands for differentiable. So we combining differentiability and also probabilistic programming. And this is a core language, we say, so it's not meant to be used directly as an end user. Now we're doing that when we're experimenting, but instead the idea is to create on top of that domain-specific languages, for example, in phylogenetics. And then that is compiled down to this core language. So you don't have to reinvent the probabilistic programming part every time we create a new domain-specific language. A little bit like everybody is not writing a new generator for handling register allocation on different assembly platform. They might use something like LLVM or some other infrastructure. Okay, there are many more. How is it used? I mean, can be used. It's very general. That's a very nice thing about it. When you want to reason about uncertainty, it's based on Bayesian statistics. But of course, the problem is to make it scale up and works in bigger models. So Stan is used a lot in different science fields, doing modeling and doing. I would say that is one of the key languages used there. We have many examples of. I mean, this is from the MIT group here. With picture was early. They have some other, inverse graphics tools, and also the recent one on cleaning data, pclean, that they are also using. So there are different examples where probabilistic programming works in practice. But often the scalability problem is one of the key things. And then we have this on phylogenetics that we are working on. And we have a paper here describing the key ideas about that and showing that it works in practice. But it's also very hard to scale up for bigger problems. So here is a small program just to get a feeling of what it is. So this is MCore, but this is taken from a paper, so it's a little bit like encoded, but it's the same thing. It's just you see it with lambdas as lambdas and so forth. So there are typically in a probabilistic programming language, there are two main constructs. It's sometimes called assume, it's sometimes called sample, where you basically can view it as you're declaring your random variables. And you're also specifying your prior. So this is the parameter that you want to estimate, and you specify what do I know right now, but this is my prior. So here we say that we have some variable A, and it's beta distributed. So what we're going to do now is a model where you are having some understanding what is the probability or how biased is a coin, and then we are going to toss a number of coins, and then we'll see how the uncertainty changes, and that would be the posterior after the knowledge about these processes. So this would be a beta distribution. So if in the middle, it's a fair coin, otherwise it's biased in some direction. So it's the probability of getting ahead. And here we just defined this function iter, and we gave it a list with some true, true, false. So true, true, false, or head, head. And then inside here, this is just a recursive function. We are weighting, so we give them different weights, and this weight together with a distribution saying your likelihood when you are observing, and here we say that this is a Bernoulli observation that we're doing. Using the beta is assumed, so we are using that as input.
Can you explain that syntax? So what is weight of F Bernoulli A1 and the current element of the list?
So the it does work with the function. The Bernoulli is then you're saying that you're observing this,
Right.
and you're observing using a certain distribution. So it's a Bernoulli distribution, but it's parameterized by A.
Oh, that's the parameter of the distribution.
Yes, and then when you're executing a probabilistic program, you're computing the weight. So this weight construct is kind of a little bit low level in a sense. Sometimes you say that we are observing this data to be, for example, observe that it's true using a Bernoulli distribution. So
Weight is basically computing the probability mass associated with that
Yes.
event.
And then you can use this in different ways depending on the inference algorithm. I mean, if you're using sequential Monte Carlo, then you're going to do resampling at certain points and so forth. And if you're running this, particularly, it will be going a little bit to the right. So this will be the analytic solution. Or if you simulate with many points in using, say, sequential Monte Carlo, it will go a little bit to the right, because it's more likely if you have two truths. And it will also be a little bit sharper. So you have a little bit more confidence that it's actually this is. So you will see if you are having more and more observation, you will see that it becomes sharper and sharper and sharper, stabilizing somewhere. Okay, so this core people is then a core language, and this is the abstract syntax for that language. If you have to just to know this if you're inside the compiler and playing with that. But the interesting thing here is that the first parts here, the first 4 lines, you see that you have lambdas for lambda abstraction for functions, let recursive way of defining mutually recursive functions, match statement for doing pattern matching, and so forth, records. These are part of this MXpert, that is the core. So these are, you can say for each of these constructs, you have a language fragment. And if you want to construct a new language, you just say which ones you want. And then we constructed this new probabilistic programming language. And we just say, okay, we wanted these from an MXpert, and then we add assume, weight, and we also had observe. So observe is actually a syntactic sugar of weight, but it's good to have this distinction in certain optimization algorithms. So this is kind of illustrates when it's used in practice how we can reuse the whole complete infrastructure, because it's man years of developing the upper part. And if you just want to construct a new language, then you can just reuse. And what you cannot do when you have embedded DSLs as easy is if you want to do smart, clever optimizations that are domain specific. So we have done a lot of optimization techniques for probabilistic programming as part of it. So here is just an example where we composed. So this is real code from the core people program. So here we have the language fragment assumed. We define that, and we have a bunch of things that we compose that from. And then we extend. So you see the syntax, we just extend and add this assume construct. And then there's a different semantic functions for doing type checking and symbolize and so forth. But that is kind of the main structure of the whole marking framework. Right, so here we composed, and there we composed the fragment. And these are partial, and I haven't shown for some of them. I actually showed the whole code for that fragment. So we have done a lot of different works here then to make this efficient. So here is one work that was published last year in ESOP, where we use this miking compiler and compile down that to what we call root people, which is an abstract syntax that can then be directly translated to C and CUDA. So this was used to make it very efficient to do sequential Monte Carlo inference. And the key things was how do we do this compilation, and also how do we generate this, what we call PPI control flow graphs. So one key thing when you're working with probabilistic programming compilers is that you need to have checkpoints. You need to stop the execution and do something. It can be in MCMC, it means that you do a MCMC move, or in sequential Monte Carlo, you do resample. And how to do this in a smart and efficient way is kind of the core part of how to make things efficient. And that is we have explored a lot. So this is one way of doing it, having this low-level representation. So made it really, we beat many of the competitors by many factors. The key thing here that is kind of the drawback of this is that it's not expressive to any kind of higher order. You cannot have higher order functions and so forth, because it's hard to compile that down to C if you go into CUDA. So you cannot have the same expressiveness in the language. So we did then, yes?
What's root people and what's the role of root people?
So root people is what we call this low-level language in C. So it's kind of a macro-based language that has these control flow graphs primitives. And it also encodes the actual inference algorithm. So then we look for a solution to be able to do this in a high order function way. So then the traditional way of compiling these checkpoints is to use this CPS, so continuous passing style transformations. So when you transform the program into this style, then you can stop the program, store the state, and then continue later on. So you can have a lot of traces running in parallel, and then stop them and then choose what you want to continue with. That's a continuation. So it's used inside compilers, but you can also program it. So like Church use this transformation, and at least web people, a little bit unsure about Church, but I think that used to also CPS transformation. It's kind of a standard, but it can be pretty expensive to do that. So a work that is still on the revision or submission, it's about doing this in a higher order language, but to just do partial CPS. So just CPS transform the parts in the program that is necessary. And we do that by extracting and separating models. And this approach, so this is a whole framework where we can have different kind of inference algorithms. So you can actually have different inference algorithms for different parts of the program. And then we have these two analyses, suspension analysis and partial CPS transformation. So the suspension analysis figure out where can you suspend, and then you transform this. So you just have to transform it, and it gives so surprisingly good. We are almost on par with the this root people performance on CPUs, not on GPUs, not compiled, but on CPUs. And that is also, of course, thanks to that Camel compiler that we use as an end compiler is very efficient. But this becomes a big performance difference if you're doing this partial CPS transformation. Another part that we are doing here is work that was going to be presented now in ESOP in the spring, is alignment. So these checkpoints, their properties, if they are aligned, you can get much better performance. And for example, these phylogenetic models, we have over the last part, I mean, a couple of years ago, we discovered that that was the technique to do it. And then you can hand transform the model to make it align. But the model is not very readable anymore, and it's like a lot of work to do that. So what this approach does is to do this alignment automatically under the hood in the compiler. So the user don't have to do it or even know that it exists. All right, so to finish up here, miking is then a framework that we are continuously developing, but now I think it's at the state where you can start to use it. I mean, also outside our group, but of course there are rough edges and documentation is okay, but not fantastic. It's a key thing is this MXpert, which is this low-level language, which is typed. And then we have this approach of language fragment, which is kind of the core idea of this whole framework. And we have been experimenting with this a couple of years now and developed several different systems and languages. And it seems to be a very good abstraction for this kind of framework. And we have a lot of different research work going on here, where I would say probabilistic programming, and also I didn't talk about the automatic differentiation and combining this with partial evaluation is some topics that we're working on in this. We are using the framework basically as an evaluation framework for research, but the end goal is that it should be a very mature framework for doing this and hopefully adopted in industry. That's
Thank you.
Thank you.
More questions?
Yes.
So you motivated the, I guess, IKEA of programming languages here.
Yeah, we are from Sweden, so yeah, it's a modular.
By saying that embedded DSLs have problems, but you didn't say too much about those problems. So I'm curious, what are considered the most significant problems there? And is the fact that you're not doing embeddings, but creating your own framework, does that pose problems in terms of missing out on tools of those languages, right? Because you're kind of on your own by the time you have to build from scratch. And do you have any solutions for that?
So the benefits with embedding is that it goes quick. I mean, that's the main thing, that you, instead of creating your own language from scratch, you're embedding it into it. And like Scala and Haskell, which are one of the most popular, I would say, frameworks for doing that works well when it works. One of the key problems is the leaking abstraction, or say that if you make a DSL, you still need to understand the underlying, which can be a bad thing or a good thing, depending on if you're familiar with that. Right? Then there are techniques how to go with this called shallow embedding and deep embedding. So when you want to do more advanced transformations, you need to go to this deep embedding, where you then reconstruct the AST, and then you're kind of not really doing embedding anymore. You are embedding, but you have to go to this level. And this is what we want to be able to do here, to be able to have this, because that you need to be able to do, serious optimizations on top of it. And then the drawback of this in external DSL, where you write it from scratch, is of course to make it, it takes more effort to do the DSL, and that's what we're trying to tackle, to make it easy to do that. Your question was also about the, a new language where
Tools, the debuggers, the editors.
yeah, I mean, these are always challenging when you're doing something new, of course. I mean, we started this as a research project in itself, right? So we are doing research on compilers. So that's why we're also doing research on how do you actually compose languages. So, but it's getting more and more mature, and we are working now, have also very close in connection with certain other environments, for example, Python environment, because if you're doing probabilistic programming, you don't want to do post-processing, for example, in this environment. You want to have maybe specify the model here, then you do the pre-processing and post-processing in some other environment. So make it easy to tightly integrate with other environments. That is one of the key things.
Thanks for the talk. So the MXpert seems to be the bedrock for all the language fragments. So I would assume that it needs to be highly expressive.
Yes.
Right. So my question is there any known limitation to its expressiveness, such that there might be some language features that cannot be expressed by MXpert yet?
I would say a good question. It's all about how easy it is and how efficient the end result is. You can, I would say, always express, since it's Turing complete, so you can always do everything, but it doesn't mean that it's a good approach. So this has been the challenge in the design. So what should we have there? So we don't want to make this blow up to be a very large language. So we've always been careful when we introduce the things. But sometimes we have been going, having a little bit too make it too minimalistic. And it turns out that if you generate that, then you have to go back in abstractions before you compile. So it becomes too low level. It's a little bit, if you think about, you can compile everything down to pure lambda calculus with the just beta reduction rule. But taking that program when it's big and try to generate efficiently on a CPU is super hard. So you don't want to have too low level abstractions. So that has been the abstraction. You can view it as, you know, if you're familiar with ML style language, as an ML style core. Yes.
Can we say a little bit more about the differentiable aspect?
Yes. So it's not right now. It's still not integrated together with the PPL part. But what we are doing, we're exploring is right now in forward mode how to combine that with how to combine automatic differentiation with partial evaluation. So you have these, say, 3 different main things of differentiation. You have numerical differentiation, which is not used really because it's unstable. But then you have symbolic differentiation, where you compute symbolic representation, and you have automatic differentiation. And automatic differentiation has some pros. Of course, it's a numerical. So you can do that for any kind of program. Symbolic, you have a hard time when you go using recursive function, for example. But if you just have small expressions, the symbolic representation becomes more efficient, as long as you then to have with dual numbers in automatic representation. So the goal there is, can we strike the balance of combining automatic representation and symbolic representation to get the best of 2 worlds? And it's important, the motivation is on these equation-based languages where we do differentiation of differential equations. So that's kind of one of the works that one of my students are working.
All right. Any further questions?